Good morning. Good morning to one and all. Uh, a very warm welcome to the G20 C20 International Conference on Interdisciplinary Approaches in Civil Engineering for Sustainable Development, organized by Jyoti Institute of Technology in association with Amrita Vishwa Vidyapeetham, BTU, CIRC, and other societies, along with Springer Nature being our publishing partner. I, Bhargavi C., Assistant Professor, Department of Civil Engineering, Jyoti Institute of Technology. It is an honor for me to host this session. I would like to welcome Dr. Neelima Satyam, who has generously accepted our invitation to deliver a keynote address. Welcome, ma'am. I request Dr. Poonam Shekhawat, Department of Civil Engineering, to introduce Dr. Neelima to the gathering. Thank you.
Thank you, Bhargavi. Dr. Neelima Satyam is currently professor in the Department of Civil Engineering at IIT Indore. She obtained her PhD and MTech from IIT Delhi and BTech from SV University, Tirupati. She worked as an assistant professor in Earthquake Engineering Research Center, IIIT Hyderabad, before joining IIT Indore. She was a visiting researcher at the University of Stuttgart in 2018 and at the University of Tokyo in 2014. She is actively engaged in teaching, research, and consultancy in the field of geotechnical engineering, particularly in geotechnical earthquake engineering, microzonation and site response studies, landslide hazard and monitoring, microseismic data processing, and rock engineering. Dr. Neelima received research grant from DST, MHRD, AICT, ITRA, DAE, NIOT, NRDMS, ISRO, and MOES. She published 150 plus papers in international national journals and conferences. Her research publications have received Best Paper Awards from IGS, AGU, and IIT Indore. She is a co-opted member of PAC Civil and Mechanical Engineering, served DST from 2015 to 2018. She has been the chairperson of Selection Committee for Next Scholarships of Japan since 2015. She is a recipient of IEI Young Engineers Award 2011, DRNS Young Scientist Award in 2011, AICT Career Award in 2012, and JSPC Fellowship in 2013. Young Women Engineer Award from INWEC in 2012, CIDC Vishwakarma Award in 2021, ISET Shamsher Prakash Mid-Career Research Award 2022, and Serb Power Fellowship 2022. She is a fellow of GSPS, IGS, ISET, and IEI, and she is presently the editorial board member of several reputed journals, including Nature Scientific Reports with impact factor of 4.996, Journal of Rock Mechanics and Geotechnical Engineering with impact factor of 5.915, etc. So on behalf of our JIT family, I welcome our esteemed keynote speaker, Dr. Neelima Satyam, ma'am. Over to you, ma'am.
Dr. Neelima Satyam will be delivering a talk on real-time monitoring of landslides hazard with case study from Western and Darjeeling Himalayas. Ma'am, could you please start the presentation? Thank you, ma'am.
So first of all, thank you so much for inviting me and for introducing to this audience. So, okay, can you see my screen?
Yes, ma'am. We can see. Yes.
So, good morning, everyone. And this is almost like 2:30 for us here. I've been traveling, so that's why I could not put my video on. I have some, very weak internet during this travel. So thank you so much again for inviting me to be one of the speakers today during this particular conference. And my topic will be on landslides, and which I've been working since 2016. And today I'll be specifically taken a particular case study so that I can, explain in detail to the audience or the mostly research scholars and the MTech students who may be interested in this particular piece of work. So what we have been doing is like today's presentation, I'll be focusing on only rainfall induced landslides. because landslides can occur maybe because of rainfall or earthquake, or maybe because of both also. So this is a case study at the area called Kalimpong, which have been doing real-time monitoring since 2016 with the support of NRDMS. So this piece of work has been carried out by my former students who are doing postdoc as a Humboldt Fellow and other places. So I should acknowledge Dr. Meenu and Dr. Abhi for putting their efforts in making this particular piece of work which I'm presenting here. So this is actually overview of my work on landslides. Especially I'm working on landslide forecasting, susceptibility, and also monitoring. For a area like us, like where like around 15% of Indian landmass is highly vulnerable to landslides, it is very, and there are multiple causative factors to, in addition to natural like rainfall, earthquake. I know several anthroponic and urban development, etc., etc. In addition to that, we also have a very diversified geological settings. Like if you go within Himalayas, in very few kilometers, like within 2-3 kilometers, there's a change in the geological structure and the type of formations. So we have such a diversified, very different, highly heterogeneous mass. So we cannot make a simple methodology or a uniform methodology for the entire country. So this is actually our work since like 2016. We have been working not only on the Himalayan region, including Uttarakhand and Western Bengal, part of Western Bengal in Kalimpong, which I'll be presenting today. We are also working on the Western Ghats. Western Ghats, we done extensive work in the Kerala part. Now we are into the Maharashtra also in the area called Ratnagiri. So this is overview of my work that's ongoing. As I said, like I'm working on both rainfall induced and co-seismic landslides. So we are also working on different scales. Like we are trying to build the warning systems considering local scale and also the regional scale. So wherein like we are trying to calculate the thresholds and then validate those thresholds with real-time monitoring, and then building or like our own performance based real-time monitoring system for development of early warning. So this is my overview of my talk. So something in the same thing, of course, in a different way. So as I said, like we have so many regions which are highly vulnerable, like Himalayas. We have north, west, and eastern Himalayas. We have eastern Ghats and also the western Ghats. So like Nilgiris and Vindhyas. In addition to this, like some other areas, even like in the part of Madhya Pradesh, also we do have few regions where we do have a lot of slope stability issues, and because of urbanization and infrastructure projects that's been happening. So these are the basically 4 different components when you want to develop an early warning system. Unlike earthquake disaster, landslides, we can develop a reliable warning system because we do get some time to, precursor can be identified, and that is what is called landslide forecasting. We can't forecast earthquake, right? So, but landslides are possible because mostly it is because of pore pressure variations or the generation of pore pressures, and of course which is very difficult to measure in the real field, but we could take some other parameters to understand the pore pressure changes so that we can build a warning system. So the first stage is like forecasting, and in forecasting, like where we will predict the likelihood of probability of a failure of a slope, and then in the landslide early warning system, wherein like it should be a more holistic system where we take a lot of components, which I'll be explaining in this particular presentation. And as I said, like we do have multiple causative factors. So when you want to make any kind of landslide early warning system, so there are basically 4 components. One is like risk knowledge, then monitoring, and we have to decimate this. See, warning is a very tricky thing because you should have almost like 0 false alarms. Even if you have a few false alarms, and people will lose the trust in your system. So warning system is not so easy until unless you do a lot of geotechnical, other geohydrological aspects of the area is well understood, and you do your analysis and the forecasting for susceptibility to build it up. And then finally, the response capability. So mostly today I will be focusing on how we have been doing it in developing the warning system through monitoring. So that's what my focus is on. So for failures like rainfall or slow failures, as I said, like I'm focusing this presentation on only rainfall induced landslides. So the basic thing, as I said, is like increasing the pore pressures, so which can reduce your factor of safety for the slope, and then eventually the slope may fail. So what parameters, if you want to do it, parameters to be monitored in the slope, as I said, um, pore pressures is not easy to monitor because you need a lot of sensitive instrumentation, and of course monitoring itself is very expensive uh, part. So how to do that for a larger area? And so what we have done in this particular one is like monitoring, we are not doing it for development of warning system. We are doing monitoring basically to validate whatever the thresholds or that forecasting models we have been using. So to validate that, we will do it, because you can forecast larger area but you cannot monitor larger area because of the cost involved, and also many challenges in the site. So we, for the first case study, this particular today's case study, I can say, so we used surface sensors, I can say. So they are not exactly surface, they're shallow, 2 meter below the surface of the slope. So we put the tilt sensors, and then which can understand the tilt in the ground, like ground deformations can be evaluated, so that we can validate our thresholds. So there are different physical events like onset of failure, how the transportation of the mass, and then deposition. So this is a physics of the fail landslide phenomena. So in this, to do this, we have a lot of data-driven approaches also, like wireless data transfer, field data in real time, which we have been working, and of course threshold evaluations, and of course validation using the real data. See, you do thresholds by taking some data, you do analysis. There are different approaches which I'll be quickly explaining. And but every model or every threshold or every algorithm that has been developed for threshold evaluation has some set of assumptions or some issues with the data. So there will be some false alarms. But if you want to build a warning system, you cannot have any false alarm. So what we have done in between here is like we instrumented a Act 2 landslide, and then we took the data almost like 4 years, and then we integrated the monitoring data with the forecasting models, so that we can develop the effective or reliable warning system. So for the forecasting framework, so as I said, like we are this presentation only on the rainfall precursor, and we need thresholds. So real-time data, we field data carefully evaluated during the monsoon, before the monsoon, during the monsoon, and also after the monsoon, so that we can understand what is the critical rate of tilt in the ground. So for the first, this particular case study, today's presentation, this is the methodology, which is a local scale study, because the area is very small. There's a small town called Kalimpong, which is one of the beautiful tourist place in the extreme north of West Bengal. And what we have done is like, we applied process-based models like Shitron and TRIGRS. So wherein like we'll evaluate the factor of safeties and the slopability issues, change in the pore pressures, etc. And for that we also collected huge amount of data, landslide inventory data. Actually, we don't get a landslide inventory data just like that. You need to work on it. Sometimes some people write very frequently like, we are working on this particular region, can you share landslide data? So it is not reliable also if you ask somebody to share the data. So you have to build your own inventory. We do have a lot of sources, GSI reports and other sources. So it has to be built by. So we developed our data. Then rainfall data, initially there was only one rain gauge in this study area operated by GSI. So later we installed our own weather station with a digital rain gauge, and then we started getting our rainfall data also. Because unlike earthquake, rainfall is also very dynamic parameter. It's not only rainfall intensity. You do have different rainfall parameters which will be considered when you are trying to understand this rainfall threshold forecasting models. So what we have done is like for the forecasting, so we used like different thresholds developed using intensity, duration, ID thresholds, even duration, ED, antecedent rainfall. So because always pore pressures are, completely based upon the whatever the rainfall that happened in the previous days, right? So antecedent rainfall is important parameter. We also applied probabilistic methods and some, hydrological methods like flare, and also advanced algorithmic models like sigma. So what we have done is, like, I think I can say this is the first study, okay, wherein, like, uh, we applied all the available threshold models on a particular site, starting from empirical models like ID thresholds to the highly advanced algorithmic models like Sigma. And then we try to compare that with the real-time data to understand the how to reduce the false alarms and, of course, the performance of each model. I hope you are understanding. If you're not, like, we can have the question and answers at the end. So finally, then, we instrumented the part of this region, because instrumenting a complete town is not at all easy. Um, in field, we do have huge amount of challenges. Of course, one is we are short of fund. At the same time, safety of the instruments. If you leave a pole or iron piece of rod or something, so someone will take it up and sell it for 100 rupees and then go off. Okay, so it is highly unsafe in the field to leave something, and we are instruments costing, a couple of lakhs, we are just leaving at the site. So in this field, challenges are always there. And then we finally, so it's impossible to monitor the entire town, right? So what we have done is, like, we have done extensive field visit. Then we selected part of the highly vulnerable slope. I'll, like, show you those photographs and how we selected that. And then, we have done some studies over there, field studies. Then we instrumented the sensors. So many times, people ask me, like, how do you identify where to put a sensor? Okay, how deep to put a sensor? Of course, in our case, we put a tilt sensors at around 2 meters from the surface. But where to put a sensor, and what is the density of the sensor network, so how to evaluate, and all these things. So this is one of the very critical point which we need to do calculations before instrumenting. Many times what happens is, in the past also, I have seen some of the case studies from around the world. So there are cases like people put an instrument, but they don't get any data. So you had, but there is no data coming from that particular site. It's all waste of time and effort. So what we have to do is, like, what we have done is, like, we have studied extensively, the field studies. Okay, a lot of tests have been carried out, and then we optimize that locations based on this. I'll explain. So once we have done all the three parts, then we try to look at the performance enhancement of these thresholds. So we try to enhance this threshold models, and by incorporating real-time data into it, and then we try to see its performance of each model, so that we can say that which model performed better for this particular site or the region of study area, and that will help us to build a reliable warning system also. So coming to the details of the study area, as I said, it is in the extreme north of Western Bengal, state of Western Bengal. And here you can see here, it is like a tabletop. Okay, so, like, it is a curved tabletop, something like this, wherein, like, you have Tista River and Raleigh River on both the sides. Like, on either sides, two rivers are flowing. And so if you see that this is like a tabletop and curved tabletop, and you have a river at the bottom, and you have another river in this side, and there's a lot of river erosion at the top. Fine. And this is the western slope in this region, which is in the box, this side, and from the other mountain. And you can see here, these are the blue lines, these are like water. What happened is, like, as I said, this is like a curved tabletop. So, and it is a very tourist attractive place, and also educational hub in that region. So because of that, a huge amount of constructions happens on the top, and also along the slope. You can see the constructions on the slope also, right? And what happened is, like, because of huge amount of increase in the built up area, so obviously that whatever the streamlets in that region, they are just gaining the energy, and they are just flowing on the either side of the slope. So these blue lines, which they locally call that streamlines, they call it as joras there. So these are the joras, natural streamlets, and they are just joining each other because there is no water can percolate inside the top, this part, and they are just joining, and then during the flow down, so you can see the erosion along the slope, right? And the red color line is this particular area, which is a Chibo area in this region. And this area is highly fragile. Okay, and there were some schools also. You can see here dots, something like that. So these are all very very fragile regions, and any small already there are cracks in the buildings, because the kind of progressive failures do happen in this region. Then the orange line is where we put our instrumentation. I'll show you that in my next slides. Okay, and then this white line which you see here is like is a track line, wherein like we move down from top to bottom. So our just a GPS track, etc. Okay. Um, So this is actually the details. As I said, like it is like this is the top. Hugely, a lot of construction. Even 5-story hotels were being constructed in this region. And this is the drainage part. And of course, this drainage diagram is not up to the scale. So as the built-up area, they are also building down the slopes. Okay, around, right. So they are coming this side and this side also. Is the down the eastern slope and western slope. So built-up area is increasing. Because of that, these natural streamlets, the drainage, so they are joining, and they're increasing their energy, and of course a lot of erosion, which I show you in the previous photo. So this is the national highway 10, and this is the only route. If this road goes off, obviously you get disconnected from this particular town. So it is one of the main road in this to go to this city. And then of course this is another photo from other side. So you see here, this is the state, this is the closer view of this national highway here. And this kind of failures happens. And then this is like very progressive, as I said. And the local people, when you talk to that area, these people speak not Hindi or Bengali, they speak Nepali. So a lot of challenges with the language also. Anyway, so this is a they say that in this monsoon यहाँ पे crack आ गया, and then in next monsoon this will go off. So that is their basically experience, because in this failures they have been seeing or something like that. So then first thing that what we have done here is like ID thresholds. As I said, like we started working on like all the forecasting models, starting from empirical models. So there were like conventional thresholds. So we have been, then after that we have done the monitoring, and then enhancement of this by combining these two. This is what I'm going to present here. So now I'll explain you whatever the conventional models we from normally conventional models to highly advanced models, whatever we applied in this study region. So ID thresholds, taking the data, as I said, when we started the particular analysis, we had only one rain gauge operated by GSI. So then that too, that rain gauge was giving daily rainfall data. So, but for you to generate a proper forecasting, you need at least hourly data. So starting there, we didn't get any data of rainfall, and except this one rain gauge for daily rainfall data from 2000, something around 10 to 16, because we started in 16, and before that there was no data also from any of the agencies. And then later, what we have done is like we started with existing data, so we took that data and looked at this conventional ID thresholds. So this is our threshold line, and with the ID equation. And if the rainfall duration and intensity, if it comes somewhere here, so there is a low probability of landslide, and if it is goes something like that. So similarly, even duration thresholds have been done. Okay, and we have taken some uncertainties also here. And then in the second model, what we have done is like probabilistic. We applied both one-dimensional and two-dimensional Bayesian approach for conditional probability evaluation. So probabilistic rainfall thresholds for different parameters like rainfall event duration, antecedent rainfall has been evaluated, and we found it out the probability of landslide occurrence is around 0.37 if the intensity is more than 10 mm per day when we have done the one-dimensional Bayes analysis. and it was 0.67 if it is for 3 days continuously, because in this region the rainfall goes continuously for a week also with an intensity more than 30 per day. So this is based upon two-dimensional analysis. Then we applied a hydrological model, flyer. This is it's a mathematical model, very interesting also. So what it do is, like, if you see the flow chart here, it calculates a function, mathematical function called mobility function. And this is actually site specific value. So you need to give a lot of site specific data to it. And we can have some limiting mobility value. And then if your mobility value at any, it's a real time, like, okay, it calculates a real time graph like this, okay, the like continuously. And with when you are feeding the data, rainfall data, as I said, like in 2016, we instrumented our digital rain case. So we started getting our every 10-minute rainfall data of the region. So then what we have done, like, if the mobility at any particular time, if it is less than critical value, obviously there is no failure. But if it is more, then there may be failure. And within, when there is failure also, you can have different failure scale like this, wherein, like, you can have alarm or alert or attention. So this is the overview of how this model works. So we calculated, what happened is, like, as I said, in the Chibo area, which we identified as the most fragile within the region, which is in the eastern part of the city or the Kalimpong town. So this particular Chibo region had a major landslide in 2015. Okay. So that rainfall data, we could get it. And then, we calculated and other infiltration parameters and site specific parameters after our field work. So we have considered all that. We calculated the mobility function for that site. As I said, it is a site specific property, okay, as like around 0.27 something. Okay, so that is a maximum value. So now, like in 2016, when it is a real time curve, okay, mobility function comes like this. So when we got 2016 data, okay, we use this value as a threshold, and then we try to see how the failures are happening in this region. So then, for generation of attention, alert, alarm, what we have done is, like, whatever the critical value, we multiplied that into 0.8, 0.6, and zero point 0.4. This is our uh, uh, details which we have made. So if you have your graph is touching this attention line, which is zero point 0.4 times of your critical value, then the local administration can be attentive, right? And if it touch this one, they can give an alert to the public. And then if it touch 0.8 times of the critical value, wherein you can create an alarm. Okay, so this is how, like, we can build, and this is operational model. Right now it is being operational. So personally, I like flyer model because you can get different levels of alarm. So that's only reason. Next one. So then after that, what we also applied process based models. As I said, like TRI GRS. So here what happens is, like, it calculates factor of safety. It calculates basically pore pressures. Okay, with the time or rainfall data and the real time, and then it will calculate the factor of safety like this. So in this particular thing, you can see here it is 0 hours, 24 hours, 48 hours, and 96 hours. There's a change in the factor of safety for the same region, right? So this also we try to see. Then the Sigma model, which is an algorithm-based model, and this particular model has been developed at University of Florence by my collaborator. So we applied the Sigma model on the study area, again on the Kalimpong. Okay, we're taking all the data. So this is the spatial distribution of the rain gauge and the landslide events in the study region. Then we tried to apply this, so to understand, like, forecasting, like how to create an warning. So this is a trial and error kind of method, and this is the algorithm that is being used for calibration. So what it calculates is, it calculates sigma. If you see here, different value, as I said, trial and error, different values of sigma values, 1 times, 1.5 times, etc., etc. We apply that, and we'll see what is it's a between duration versus cumulative rainfall graph that is a sigma curve. And then we try to do the trial and error in such a way that we reduce the false alarms. So you can see here this 1.5 sigma line was the best suited line based on the analysis, whereas this blue line is a false alarm. So what we have to do is, like, with our during our analysis, we have to bring this blue line closer to the dotted red line so that you will get less false alarms. So, and of course, this is a confusion matrix for a quantitative, comparison of the analysis, like with how many true positives, false negatives, and true negatives. And also, this is a comparison of the analysis carried out with sigma model with other empirical thresholds also, like as I said, like how many true positives, how many false positives, and etc., etc. And also the efficiency, specificity, and sensitivity, likelihood ratio. These are some of the parameters for calculating the performance of each model has been evaluated. So we got like higher likelihood ratio for the sigma model for the study region. So this is the first part of my thing, wherein like we put all the threshold models starting from the empirical ID thresholds to the highly advanced sigma models. Then we did the monitoring. So this is a real-time monitoring. So many times people think that going to the site, getting them data itself is a tough. This is next to that. And this is actual slope profile where we instrumented our sensors. You can see here, this is our sensor locations. The red color arrow was actually, there was some sort of sinking kind of zone here, so wherein like whichever sensors can predict the deformations in the ground. So this is actually the location. Initially, first phase, we could put only 6 sensors because that itself costed too much of money. So, and this is a system which I bought it from Japan. This is the first project wherein like we are not into system development or monitoring system development. So we took the system from a professor who developed us at Tokyo University. So we just purchased it, and then we put it up at the slope. But in Western Ghats and other locations like Uttarakhand, we develop our own system, which is highly complex than this. Maybe in sometime if I get a chance, so I can give that details as well. So then we started monitoring. As I said, we started in 2016, but after monsoon. So we don't have data of that year before monsoon. So that's why we discarded, though we instrumented on 2016, we discarded that data. What we want is like, we want to see the deformation or the ground deformations in the complete cycle, okay? Pre-monsoon, during monsoon, and post-monsoon. So then what we have done is like we started looking at the data from 2017. You can see here, this is how the data comes. So this rainfall data, and like from August to up to December, there will be rainfall, something like this. So this is the rainfall data of 17, 18, 19, and then later 2021 also then. So then we instrumented, we placed 6 sensors, right? So this is the tilt data. You can see here the red color line, something sensor 2, and other purple one, sensor 3. They had a huge change in the ground deformation, whereas other 4 sensors, they don't had that much. So that's why in this figure also, you can see here, this is the kind of subsidence kind of region along the slope. Those correspond to these 2 sensors only. So then we try to look at the data. So, and also we had some volunteer at the site, so who keeps sending the photographs and some videos in this region. So you can see here, and there's a kind of subsidence you can see here at these sensor locations, and also the cracks. Okay. So then tilt angle variations for all the sensors, we try to see here, as you see here, up to 17, 18, 19, 20. This is 4-year data here. And then later we had like some failure also. Sensor 2 was completely failed, okay, and we could not recover. And again, we placed another sensor in that region. So that was one of the, if it fails, it's very good because it gives a lot of information and help us in developing our monitoring system. So then every day we zoomed up because this data keeps coming every 10 minutes. So using VSAT and the mobile data network, both we applied here. And then this is the time history of volumetric water. We also put water content sensors at the same location where we are measuring the tilt. This is a 2D MEMS tilt sensors, wherein like along the slope, that is x direction, and perpendicular slope, it gives the tilt in the ground. Uh, so this is for different sensors. This is the volumetric content in the sensors. So then we zoomed it. You can see here our basis. We try to see what exactly is happening. This is the sinking period for the tilt sensor 2. So during this period, we zoomed it and try to understand how the behavior of the ground in this particular period. Again, this is for the sensor 3. Then we want to correlate that with, kind of tilt rate as a function of time. So before the slope, for different case studies. Actually, as I said, like this system, I bought it from, Japan. So Wang is the one who developed the system, and they instrumented the system, and it's been highly validated around the across the globe. So they have this placed in Sri Lanka, Pakistan, Brazil, Taiwan, Korea, and extensively in Japan. And of course, this particular Kalimpong in India also. So they validated trying to see this using this tilt rate, the change in the tilt rate. So we can give the caution and warning. Okay, so there is a window where you can try to see the tilt rate of the ground, and then we can try to do this. So this is the second part of the work. And now what we have done is like uh, these are two different parallels. Like one is like forecasting, and second one is monitoring. But we were trying to monitoring is not easy, as I already said, for a larger area like our country or any other country as well. So we want to integrate these two. So what we did is like we want to enhance the performance of the statistical models, so which is much easier data driven approaches. So there are two approaches we have taken. One is like using antecedent moisture content. Okay, so for that we applied a hydrological model called sheet-run, which simulate the whatever the drainage path and process in the river basins. So actually it is basically hydrological aspects of landslides, which I am going to present in this particular slide. So then partial differential equations which are governing the water flow, so they are solved using specially distributed input data. And then this is the parameters which we have considered for carrying out this analysis. And this is how we did it up using antecedent moisture content of the site, wherein like we integrated this models, statistical models, using the Bayesian approach. So this is a two-dimensional Bayesian approach. Then we try to find out the maximum probability which can become in different cases. And in the second approach, we did that using the field data, because we had extensive, very good data. And I also can say that I think this is the published, first time published part on monitoring, real-time monitoring in the country for landslides. Because maybe people are doing, but I could not see any publication out of that. So with the data, so this is the data from the sensors, which has been at the Piriti Jora, that is at the sensor 2, for the analysis. So where we are trying to see what is the displacement period and how we correlated that with the rainfall and different rainfall parameters. And then in the second part, as I said, like we try to integrate the monitoring data with the algorithm based models. Like here we applied IDED tilt we already done, and then we integrated that ID thresholds with the real time tilt data, and ED also with the tilt data. We also done with the sheet run also. What happens is like sigma also, sorry. So here you can see here, if you put only one, like idea also, you had so many false alarms, and two alarms are very less. And ED also similar. Even with the real time data also, you had different several false alarms we got. So what we try to do is like, and we miss some alarms also. So when we integrate these two, okay, so you can reduce your false alarms. Okay, so that was what we can try to achieve. But still, this number of false alarms is also not acceptable if you want to build a warning system. So then this is for the enhancing the performance of statistical thresholds. So using sigma approach, so we integrated that sigma plus tilt and only sigma, and try to see there is increase in likelihood ratio to almost like double. So then we try to, this is the highest performance wise more effective approach. We better results we got it with the sigma and the tilt. So we applied that in developing our warning systems. So this is actually some of the parameters for performance enhancement. of the rainfall thresholds. So with only ID, ED, only sigma, and with the real-time monitoring data, till data. So this is actually AUC curve. Okay, so for understanding the performance, so final output was here like as I said, like after doing extensive forecasting, applying different forecasting models, and also on the monitoring data, integrating these two, we could build a different levels of alert. That is red, action is required, orange, and yellow. Of course, with the green, no warning. So we also considered both long term and short term rainfall effect. Okay, so for both shallow and deep seated failures in this particular region, because it has all type of landslides, it has even the debris slides also. So then additional control to minimize false alarms with the ground based monitoring system what we instrumented, so that we have done. So real-time monitoring of an active landslide, which we did it in the Kalimpong. So some of the conclusions. So first part is thresholds. So wherein like we applied all the threshold models that are available from empirical to highly advanced models. But we found that Sigma model was giving us highest efficiency. And then, but there is chances of false alarms which can be implemented if we combine with the monitoring thing. So this was the limitation if you have only thresholds. Whereas if you have only monitoring, then there is another limitation that it can be influenced by some anthropogenic factors, or it can also generate some false alarms. So what we have done is like we combine these two to make a combined approach, wherein like we propose the new method by integrating this forecasting models and the real-time data. So it's algorithm-based approaches we applied, and wherein like we can overcome the limitations with these two methods separately. So this combined approach with the Sigma and integrated that with the real-time data give us the best performance in developing the landslide warning system for this Kalimpong. And this is in the operational warning system that we have, and it gives in 4 different alert levels, and it can be even in the mobile also. So this is from my lab, and just for introducing, like I do work not only on landslides, I do work on earthquake also, geotechnical earthquake engineering. That is actually my prime area, wherein I work on basically on liquefaction and mitigation. So soil sector interaction. I also work on pavement and sustainable geotechnics. So this is my research group at IIT Indore. So thank you so much. If I have any questions, I can take.
Thank you, ma'am. Thank you. Disaster mitigation is one of the very important criteria of our conference as well. It was a very informative session, ma'am. Are there any questions, please? I would like to unmute the participants if you want to ask any questions. Any questions, please? Yes.
Ma'am, hello.
Yes, please go ahead.
Hello, yes.
My name is Rajan. I had a question. Is there any criteria for deciding the installation of the sensors, like the spacing or the depth?
Oh, okay. Actually, this is a very important question, and it's not easy to address also. Why? Because it is one first thing is like it is site specific. If I say that I put 6 sensors in an area of around 300 square meter, so or 800 square meter. So that doesn't mean like this is in Kalimpong, but you may need a dense network in some other region. Okay, so it depends upon geological, geotechnical and hydrological aspects of your study region. You need to do a lot of field tests. What we have done is like we have done ERT. I think recently somebody asked me here also in Japan 2 days before the same question. So we have done extensive field visits, right? And we have taken some bore log data also. We try to understand the substructure heterogeneity. Then we applied an optimization model, because obviously the number of the funding is limited, so obviously we cannot put too many sensors also. So that's all. So we applied all that and then used effectively. Even you might have seen, even in spite of doing all that, initially in the first 2 years we didn't get data from 4 sensors. Okay, so only 2 sensors were giving us data.
Ma'am, these models are 2D models or 3D models which you have used?
Yeah. No, actually they are 3D models mostly, except a probabilistic one-dimensional model we applied, and ID thresholds they are conventionally one-dimensional. Others are like sigma was a 3D model.
Okay. Any slip circle analysis was done in this case, madam?
Yes, that we have taken care for installing the sensors. As I said, like we have done extensive, field work and analysis. So it was a part of that. We collected sample, for C5 values, a simple, slip circle, factor of safety evaluation. These are all been done to identify which is the most critical area or the location to put the sensor. That I didn't explain over here.
Okay. My last question, madam. What is the time that it gives the alarm? It sets the alarm, the
Huh.
timeline.
A timeline, as I said, like, right now you can get it almost like, it's not, I can't say specifically particular 1 hour, 2 hour. It's not like that because in the same area, see, western part only we put instrumentation for the entire city or the Kalimpong, we didn't instrument, right? But we are applying that, extrapolating that date thing to the entire region. So within the Kalimpong also, the eastern part is not having the same as western part. Okay, so they're different. What we had, like in one particular case, like in the western part we are getting almost like before 2 hours we can alert. Okay, but whereas in the eastern part we could not alert that effectively. Okay, so yeah, it was like, only 40 minutes before or something like that. But when we integrate both, statistical models and of course real time data for a region like this, at least, like, we can have some good warning system. It's not like warning system you build somewhere and keep it at every place. It's not like that actually. To It has to be, developed or built for that region. I can tell you the other cases because I just took only one case study here. We have done extensively for two districts in Kerala after 2018, Kerala landslide disasters in Idukki and Wayanad. You can see, check our papers if you're interested. So there, like, we had, because there are a lot of dam authorities and also we have several, dense network of rain gauges. So we applied different methodology for that and we could do it a better way. There we didn't do monitoring at all, but we have developed very dynamic landslide early warning system there, okay, which is there with the Kerala State Disaster Management Authority people also. So we have been actively working with them. So what I try to say, warning system building, this is one thing that we have done for a particular region, right, where we did integrated both this. But we did something different in Western Ghats. Of course, without monitoring, we have developed a dynamic susceptibility, landslide susceptibility, in the sense like it gives you susceptibility map with time. Okay, it changes. It's not like, what happened at present is like we have one susceptibility map which has been developed 10 years before or sometime back, and then people are using that. In 2018, that susceptibility map existing in Kerala, wherever the no landslide region had huge landslides. Okay, so for warning, early warning system in that region, what we have developed was a dynamic susceptibility map. Okay, it changes within the day also, right, based upon. So it automatically changes. So and using that dynamic susceptibility map, we developed a warning system there, but we didn't do monitoring. Okay, so I mean to say, warning system is something which can be done for that particular region by doing extensive study. I hope I answered your question.
Yeah. One more, madam. One more question. Can this technology be applied for dam structures also?
Yes, Uttarakhand, we are working on that only. Uttarakhand, what happened is like after this work got, published or whatever. So I was called and I was given a project. So for Uttarakhand, and I don't want to work on Uttarakhand that time because, it's already some people have been working on Uttarakhand and something like that. So, but, we have instrumented sites near Joshimath and not before. This has been started in, I think we started 2022. We are getting data June 2022. Like later, recently, Joshimath sinking and all these things came into picture, right? But let me tell you, there are maybe 200 such kind of towns in the northern Himalayan region which is facing similar to Joshimath. But Joshimath had that focus or media focus which you got. But similarly, 200 plus cities may be thinking like that in that region. Okay, so in Joshimat, we had a different approach. There we have earthquake also as a causative factor. We had done some combined analysis, and our network, it's here we have applied only and but where in Uttarakhand we have, we instrumented, at the deep 30 meters also we have a very dense network of extensometers, inclinometers, piezometers, strain gauges, rock, and also micro earthquake monitoring system. So it was a very complex thing, and we are working on that. Maybe by next year we could complete the project.
Thank you, madam.
Thank you so much.
Thank you, ma'am. Thank you for joining us. It was a very informative session, something which all of us need to know. Thank you. Thank you for your time, ma'am. We are very humbled by your presence here today at IACEST.
I just left my email ID also in the chat box, and interested students who are interested, they can, contact me, and I'll be very happy to interact. And thank you so much.
Thank you,
Thanks
ma'am.
to organizers as well. Thank you.
Thank you so much for joining us, ma'am. Thank you.